Hello and welcome back to Calculus 1, section 4.9 on integration. So this is the last section in chapter 4, but it's introduction to integration, which is that third and final stage of calculus. Being calculus is split between those limits and derivatives and now integrals. And the story of the integral is not too old, like, 300 years, if so. So, Newton knew nothing about this. I mean, some things, because he was insanely smart, but none of this notation existed. Like the notation with this sign, like that's not even 200 years old. So a lot of stuff that, right, you're kind of catching up. I hope you are you are getting that. You started this course in 1600s, and now you are already, pushing like the early 1800s. Okay, so you are rapidly catching up. When you complete your Calc 3, complete your differential equations, then you will be about 150 years behind current mathematics. So that's kind of, but it's a rapid catch up, right? Something that you did over time, given that one course covered like 200 years span, right? So it won't take you long if you want to get to current levels, a couple of years. Anyway, talking about integration, so and why integration is so important and so on. Well, let's start first that integration are, backwards derivatives. So we're going to see how that works. And then I will make sure that you know that your Calculus 2 is going to be half on integration. More than half, maybe even 2/3. Yeah, 2/3. That's good. 2/3. 2/3 integration and 1/3 limits. That's your Calc 2. And you will say, am I going to take any derivatives there? Yeah, you're going to take 7 derivatives in Calc 2, okay? That's it, 7. So we are going to use them also in Calculus 3. They're going to be used also double and triple integrals to calculate volume and a whole bunch of other cool stuff. It's used all over the world in sciences and so on. And we just want to discover first what this is. And then our chapter 5 is going to take a look into the theory of integration. And immediately when you hit Calc 2 with the chapter 6, you're going to do some applications and then some more techniques of solving integrals and so on. So the goal for today is to understand what the antiderivative, i.e. Indefinite integral, does. So if I have the derivative of x squared, and we know that the answer for that is 2x, whether you are using the formula or you went through that long procedure with the limit, we can say that the procedure that will undo this transformation, which is transformation from x squared to 2x, is going to look that the integral of 2x dx is going to provide x squared. Now there's more to it, but we'll get there. Right? For now, I need you to see that the derivative is reading this way, integral is reading it this way. So when you take the derivative says the derivative of x squared is 2x, and then the integral says integral of 2x is x squared. So it is this backwards technique, and it's named the antiderivative, kind of tells you that, right? It's really straightforward. But we are not done here, because if you observe this problem, you immediately see that we have an issue, right? Why would this one give you x squared? Sorry. Why would this give you x squared and then the same thing give you x squared plus 10? Right? So you see the issue, you see the dilemma. The problem is that these derivatives destroy information about constants. right? Because there is no change in 10. When you try to measure the change in a constant 10, the change is 0. But also, if you try to measure change in -7 or any other number, it will also be 0. So the problem is that we can't really undo this derivative fully, because we never know if there was a constant or not, which is why to each integral that we solve, we add this plus c. Now that c, as you can see, in the top problem refers to 0, because the constant was 0. And in the second problem, that is c is 10. And we will have a way to calculate that c if initial point is given, but we have to actually build up to that point. So now, given that we have this situation, I can write somewhat of the formula that integral of f of x dx is going to be capital F of x plus c, and this capital F of x will be known as antiderivative. Now, this immediately means that the derivative of f of x plus c is equal to f of x, right? So that's that part. So this is what we have for our calculation, right? This is what we have for our calculation and the way to check the problem, right? Check the problem. So this is something that we can now do, and which is undo derivatives. Now the issue is that you will run into functions that are extremely difficult to integrate, and you will also run into functions that are impossible to integrate, which is why we literally have 5 chapters of integration, right? When you take a look at integration chapters, you have 5, 6, 7, 8, and 9. Well, 9 is differential equations, so 4 chapters, okay. 4 chapters of integration, and only 2 chapters of derivatives, right? Chapters 3 and 4. So double the amount of chapters on integrals, and it spans over two calculus courses. Now, your Calc 3 is a repeat of Calc 1 in 3D. So yes, you are learning some of the new concepts, but a lot of stuff in Calc 3 will be extension of Calc 1, which is why Calc 3 tends to be labeled as the easiest of all calcs, because you're technically recycling Calculus 1. But there will be an entire chapter of Calculus 3 out of, I believe, 5 chapters there. One is completely devoted to integration, chapter 16. So integration is this big idea, and it's very important because it gives us different explanation on what the I twisted my own words and now I can't get out of it, so I have to go back. So derivatives measure change, and calculus measures a different thing, which is called accumulation. So if we are going to talk about, let's say, population, I can come up with a population model, and I can differentiate that model, and that will give me opportunity to calculate how much, let's say, people or rabbits, whatever, how many new people you add or lose in particular year, depending if the population is going up or population is going down. So derivative will measure the change, which is technically just the difference added in that one year or subtracted. Now, in terms of integrals, they measure accumulation. So they are giving you the total amount of people or rabbits alive. They're not telling you just, oh, here is the change. This is how many more you have. No, integrals accumulate everything. And you will see that you can use them also for kinematics, for velocity and all that stuff. You can also use it in business. You can use it in physics. Let's say energy under the curve is going, area under the curve in physics in certain graph is going to be represented as, which is energy, and it's going to be calculated by the integral. So a lot of applications, it is an entire branch of calculus. And as you can see here, it is very closely connected to the derivative because it's literally just backwards, right? Now, as I said, not every function that you can think of and stuff in the integral, not every function is going to be possible to integrate. Is everything possible to be differentiated? Yes. We have the rules for differentiation, and depends on how annoying the problem is, we might use the sledgehammer, which is logarithmic differentiation, or maybe we can just use the measly product rule and be done with the problem, right? So technically, anything you write down as a function, you can differentiate using one of the rules or combination of the rules that we learned in chapter 3. Now, that is not longer true for integrals. Even when you go through chapter 8 in Calc 2 and you learn all of these techniques to integrate, trigonometric substitution, integration by parts, partial fraction decomposition, blah, 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 blah. Even then, you will be you will very easily run into a problem that none of the techniques meet, and that's what we are going to do in chapter 11. You are going to run into all of these integrals that cannot be solved by computation, in which case you have to refer to numerical methods, and that's what chapter 11 is going to fix for us, well, for you, because I'm not in Calc 2 next semester, so you'll have to do it without me. All right. However, you can stop by and ask questions. I mean, that's fine. Even I'm not teaching Calc 2, but I still know it, and if you are in trouble, you can stop by. All right. So, let's go and think about this a little bit. What is the integral of cosine x dx? Now, guys, the way you should be thinking is what goes in a box, and you always put plus c at the end, what goes in a box so that the derivative of that thing is cosine? Can anyone offer that solution? So what should go in a box when differentiated gives me cosine? Beautiful. Sine x. This is what integration is all about. Now, yes, we're going to have later on procedures and things like that, sure. But, you know, this intuition is very important. We can make this a little bit harder. You might disagree, but let's see. What is the integral of x to the 7 dx? So technically, what goes in a box, right, whose derivative will spit out x to the 7? Anyone? It's okay to be wrong. I mean, you are learning and you are trying. Even the partially correct answer would be good enough. Because at that point, we just have to fix one thing and we're done. One 8x to the 8. That's perfect. And some people might be going like, what? How? Well, think about it. Every time you do the integral, you can use derivative to check it, which is why I always like integrals better than derivatives, even though they're much harder. Because, you know, for derivatives, you really have to redo the problem. There is no checking it. You just redo it and hope to get the same, right? Or you check with other people what they did and you compare it. But for the integral, right, once you integrate, you take the derivative and you make sure that you got your problem back. So you copy 1 over 8. Oh, by the way, the derivative of c is just 0, so I didn't even write it. I should have, but yeah, what the hell, let's say it plus c. So you copy the constant, then the derivative is this, plus 0, which is derivative of c. These guys cancel, and you just get your x to the 7. Yay. Very simple to check this. Okay, let's go and take a look at crazier situation. Square root of x dx, right? So what goes in a box plus c? It's not an easy question, right? It's not an easy question because now you're thinking, wow, what goes in a box so that I can have my root x as the answer? Technically, you're asking the derivative of what is equal to square root of x. And that is a very tough question to answer. I mean, it's possible, depending on, you know, how well you know your math. Because you can hack into the fact that you have this and this and this and equal to some form of the exponent, and you know that this one is n and the other one is n minus 1, right, and play that game. So again, depends on your determination and the, you know, willingness to spend time to figure all of this out. Sure, right? But the question is, like, can we just write the rules down like we did in derivatives and try and figure these things out? Okay, the YouTube just got it. So let's go and take a look at the rules, and then we can just fill in these blanks, fill in the blanks easily. So integral of 0 is just a c, because integral of 0 is 0, and you always have that plus c floating about. Now, does this make sense? And the answer is hell yes, because the derivative of any number, right, constant is 0. There's no change, right? You're trying to measure the change in a constant. Well, the change is 0. Very simple. So there goes our first formula. The next formula is the one that you really want to know. And that is x to the n plus 1 over n plus 1 plus c. Guys, this formula covers 3 different types of functions, including our problem right there. Because the x to the n could be polynomial, could be rational, could be radical. Polynomial, x to the 9. Rational, 1 over x to the 6. Radical, cube root of x. Because these guys can be rewritten, right? The 1 over x to the 6 can be written as x to the minus 6. And the cube root can be 1/3 as the power. So now when I go back over here, I say, that's how I do it. Okay, let's go. We say that this is x to the 1/2 dx, and then we use the fact, like the +1 on the exponent. So that's going to be x to the 1/2 plus 1 over 1/2 plus 1, everything plus c. And now that is x to the 3/2 divided by the 3/2 plus c. And then when you deal with the double fraction on the bottom, you get 2x to the 3/2 divided by 3 plus c. So this puppy has this as an answer. And all we did is we used the formula that you see on the bottom. Now, it was used for radical, where I wrote the exponent as a fraction. And then I had to add 1 to the fraction, right? And have the answer to get 3/2 exponent. Now, if you are still skeptical, right, and go start yelling about, conspiracy theory in mathematics or something like that, just take the derivative, right? Don't embarrass yourself. Take the derivative and you will see that you will get square root of x out of this mess. C goes to 0. We don't even care about that. But, right, so if I take the derivative of 2/3 x to the 3/2, I will copy 2/3, which is the constant, and then I will have the power 3/2 drops down, and then I subtract it by 1. I get 1/2. When fractions are copied, I guess 1/2, which is root x. There it is, right? So every time when you do the integral, if you want to know if you did it correctly, all you need to do is to differentiate back. I mean, if you get something that it doesn't look the same like your problem you started with, or it's not algebraic equivalent to it, then obviously your integration is wrong, given that you can do derivatives. There's nothing more frustrating, right? When you do the integral correctly, then you check it and you mess up on a derivative, and then you think your problem is wrong, and then you go and you ruin the perfectly right problem. I mean, I have seen that happen in the past. So, yeah, make sure you can do your derivatives properly, so we don't have to worry about that being an issue and brought up in class, right? Okay. So we have this. Then we have our good old friend, we have our good old friend e to the x, which spits out the same e to the x, because the derivative of e to the x is itself. Therefore, integral, which goes the other way, well, if you have mapping of e to the x into e to the x, then you can reverse it and still have e to the x into e to the x. And that's that. Now, there is a formula. I guess I can go, well, actually, all of these formulas should be read when I think better about it, because these are the formulas that you guys will be using for years. Not just math, like any course that contains calculus in it, like these are the formulas to solve. Now, for this one, we have the better problem that has the number in front of this x. So I put ax, so 2x or 3x or 10x, whatever, right? Negative 10x, whatever. And that's going to be e to the ax over a plus c. So that formula is better because you are most likely to see e to the 2x and stuff like that rather than just e to the x. So, I would go with the purple formula. Then we have another creature, and this one is scary. We'll explain why later. Scary because, actually we can talk about it now, because you forget to put these absolute values. You can see them in a formula, but then you don't put it when you don't put those when you're on a test or something. Then you get, you lose like 2 points or whatever, and then there is a lot of screaming after that for 2 points. Now, currently, it costs you 2 points. Later in Calc 2, costs you much more if you don't have these. So they're not optional. They're not there for decoration either, because those absolute values fix the issue of the domain. You cannot say that left side is equal to the right side unless they have a part of overlapping domain. So, when you take a look at this side, this function you know graphs like this. That's a terrible graph, but something like that. And you can see that your negative infinity to 0 union 0 to infinity is your domain for 1 over x. Now, if you look at ln x without absolute value, that one is only 0 to infinity. So now you see the issue. It is perfectly fine for you to pick negative 2 on the left side. Well, if there are no absolute values, can you actually plug in negative 2? And the answer is no, because it's not in the domain, and your answers will end up being complex numbers. But if you have the absolute value present, then all of a sudden, the graph for ln looks like this. Has 2 branches that do this. So the 0 is still the vertical asymptote, but hey, we had that 0 vertical asymptote here as well. And you can see negative infinity to 0 union 0 to infinity again in there. So, right? It is not there for decoration. When I pick a negative number now, in this one, I can also pick the negative number in the other one. That's why that absolute value is there. And don't let me catch you without it. Bring the absolute value with you when you go somewhere. Now, the entire section of Calc 2 called, I mentioned it, partial fraction decomposition, pretty much every other answer in that section will be some ln of absolute x plus 3 or something like along those lines, okay? So you will have 2 or 3 of these per in one problem, right? In one solution, you will have 2 or 3 of these. So if you miss this on each one of them, like obviously every single one of the problems is incomplete and not correct, because there are issues that, right, without those parentheses and whole bunch of other stuff, right, the solution would be invalid, even though to the untrained eye it shows as valid. Okay, let's recap. So integral of 0 is just 0 and then plus c. Then you have the polynomial rational radical x to the n, which is x to the n plus 1 over n plus 1. Then you have your e to the x with the better one, right? Because if your a is 1, you see this a goes to 1, so you still get the same, like the red one. And we have now 1 over x that will give us this ln. All right, so now what are we doing next? Well, we have 6 trigonometric functions, out of which only 2 are basic for integration. And this is where some people lose their cool. The integral of sine x dx is negative cosine x plus c. You will say, well, wait, wasn't it backwards? Yes, it was backwards, but this is backwards. So sure, it's going to be backwards. See, the derivative of cosine is negative sine, and then this negative will make it into a positive. So this is a solid formula. Another one is cosine x dx, which now gives just sine x plus c. Think about the derivative in this way. Derivative of sine is cosine. Think about the derivative on top, going this way. Derivative of cosine is negative sine, and then negative and negative make it a positive sign. Okay. The next creature is not going to be a tangent, because the tangent is not a basic integral function. Can you do tangent? Yeah, in 5.5. In this course, in 5.5, you will learn how to deal with tangent graph. So that's all good. So what are then the missing? If I'm not allowed to use tangent, then cotangent should go into the same box, and then you can run the same argument for the other functions. But here are the basic ones, the ones that you can undo into a basic function. I mean, sorry, not undo, integrate. Well, yeah, it's undo button for derivatives. Cosecant x cotangent x dx is equal to negative cosecant x plus c. And finally, secant squared x dx is going to give you tangent x plus c, and cosecant squared x dx is negative cotangent x plus c. Look at the basic functions for trig. They are not single tangent, single cotangent, single cosecant. They are mixed in, because the opposite formula for trig, if you learned it, for the trig knowledge, I guess. When you look at this one, it doesn't have a basic sine, it doesn't have a basic tangent. They're all pushed together. Now, I can just say, because the derivative of secant x is secant x tangent x. So if I am running the derivative, I go this way, and if I am trying to do integration, I'm going the opposite way. Did we forget any of the functions? No. In Calc 2, you're going to learn a whole new set of functions called hyperbolic functions, and all of these rules will apply there as well. So it's like a list of rules, and you can just make it longer, and but it boils down to how well you know your derivatives, essentially. Now, notation. We all have our triggers, and the notation for integrals is definitely one of mine, so I'm hoping you're paying attention. Integral and dx are inseparable. And moreover, if I'm to put f of x in there, there is a multiplication in between f of x and dx. Now, a lot of people that are just mechanically learning and memorizing the course, they're going to miss this gem of information right there. There is multiplication in between the function and dx. Now, we are set to prove this in 5.2. So if that's not, that should be next week, Monday. I think so, I hope so. Oh wait, no, today's Monday. You have your Wednesday class. Might be even as far as Wednesday, we'll see. I mean, not as far, as soon. That's in 2 days. I'm flipping these things. All right, so this dx, I want you to contrast that for d over dx of some function f of x. Do you see how in some sense you are dividing here by dx? Or in this case you are multiplying it? Division over here, multiplication over there, they're polar opposites of each other, therefore, right, clearly we have this to be the opposite operation. Some notation. You have to have both of these. You can't just ignore them and not write them because you are saving on time or paper or whatever else, right? This notation is universal notation in every single part of the world. It's calculus, it's uniform language, right? Universal, I mean. So when you write your problems, because there is a multiplication towards dx, you have to put parentheses if you have multiple terms. Otherwise, you are breaking the notation, and the statements you are making at that point become, say, no bueno, right? So what do I mean by this? Well, look, if I have to integrate, well, let me finish this off. So if I have to integrate x squared plus 3 and I just put dx like this, well, I'm in trouble. Because there is a multiplication here, and by order of operations, this gets done first. But we know that both integral sign and dx need to be available for both of these. So this is the proper way to write it. If you have multiple terms, use parentheses. Let's write that in blood. If you have multiple terms in the integral, f of x needs to go into parentheses. Now, we haven't done the three very simple rules yet, but you know, I can tell you that these two can be integrated separately. So when you integrate, you get this. You get this. Now, you are already hinting on, oh, okay, we can do integration the same way we did derivatives, right, in one shot, without splitting them into separate equations. Yeah, and sometimes it is useful to split them, but in this case, it's not. Okay, now let's write those properties. Number one property is linearization. So if you have, not linearization, linearity. There we go. So if you have integral of f plus g, now remember, I have two of these two functions, right? Hold on. So it could be addition or subtraction. So this formula now will tell us that we can separate these two with whatever symbol was in between them, and then work on each one independently. And yeah, that's the property number one. And second and the last property, I can put more if you really want to, is the constant multiple. So second one is the constant multiple. So let's say k times sum f of x dx. So you can kick the constant in front of the integral and then just focus on what's inside. Oh, let's see. There we go. So you saw me just kick this one out. That's all it is. All right, so now armed with this knowledge, you can say integral of 3x squared plus, I don't know, 16x minus, now we know this needs to be all in parentheses because I have multiple terms. Terms are separated by plus and minus signs. So 3x squared plus 16x minus 12, whatever, dx. So you are supposed to, come on, tablet, there we go. So you're supposed to break these apart and try it. Now remember, it's not always, well, I'll let you discover things. Okay, I see that YouTube is providing the answer, and I like it. And I have to say that plus C at the end, that makes me very happy because you guys generally, in Calc 1 you kind of lose a point here, lose a point there for not putting that plus C. But when you do that in differential equations, you'll see you get absolutely slain. Absolutely slain. The whole part of the solution is missing because the plus C was not there. Now, obviously, more of that when you take that class. Right now, I just say, yeah, you put plus C, you don't put plus C, you lose a point. Right over there, you lose almost the whole problem. Anyway, the rule up there said that we can break this into 3 separate integrals, right? Anytime you have the operation, you can split it up. And then we can also split up the constant. So here is the step that usually no one writes. After a certain point you learn the integration. But 3 integral of x squared dx plus 16 integral of x minus 12 integral dx. Ooh, there's nothing there. It's not nothing. There's number 1. There's number 1 in here. It's never nothing. Because if you put nothing in the integral, you know what you get right on the other end. So it's not nothing. There is a 1 in there. All right, so we have 3, and now we're using that 2 plus 1 idea, plus 16, and here is my x to the 1 plus 1 over 1 plus 1, minus 12, and now the $1 million term over here, right? What is the integral of this? And the answer is it's just x. Now I will explain that, and then we're going to have the plus big fat C, right? Which think about it. If this produces C1, and this produces C2, and this produces C3, how about we just combine them all into a single plus C rather than, being annoyed in every separate problem, every term, right, separate. So now 2 plus 1 is 3, that cancels. I have x cubed. Then this cancels down to 8, x squared minus 12x plus c, and this is what we have as suggested as the answer in YouTube. Now, some of the confusion in the early days and years of calculus is why is integral of dx just equal to x plus c? Like, why is this? This is not a formula because this actually belongs, I shouldn't be doing this in red anyway. Guys, this belongs to the formula of x to the integral x to the n dx is x to the n plus 1 over n plus 1 plus c. So this is where it belongs. But now you'll say, no, I don't see any x's in here. But see, there is number 1. So you can write this as 1 dx, and then number 1 you can write as x to the 0 dx. And now when you unleash this formula, it's x to the 0 plus 1 over 0 plus 1 plus c. And that's clearly x plus c. So even though you don't see it, the number 1 is there, and because 1 can be written as x to the 0, right, you can go through these calculations and come up with this formula up there. So now, knowing this case, what is the integral of 4? Well, you can say immediately it's 4x plus c. Now, which way your brain got to that point, that's going to be between you and your brain, right? Because you have options. One option is to say, oh, kick 4 outside, integral of 1 dx, which is 4, integral of x0 dx equals to 4x plus c. Awesome. The other one is like, oh yeah, I remember what he said in the class. So if it's just a number, it's immediately that number times x, which is this variable, and then plus c. I don't care, right, which way you are going to remember this. It's just going to show up in a lot of problems, because a lot of problems have a constant at the end. Think about your, I did mention earlier, right, velocity and so on. Think about your velocity formula, right? It is going to have that plus v0, right? And that behaves as if you need to integrate it, that behaves just like this. So it is important to have these things in order. Integral of 3 over x to the 6 dx. So I'm going to give you a few moments to solve that. Now, I understand you are learning this for the first time, but this is, believe it or not, enough time to apply 2 rules. Kick 3 outside, write this as x to the minus 6, and unleash the plus 1 n plus 1 formula. So it is immediately recognizing it that this is the problem, and then you just go from there. So what do you have? You have 3 x to the minus 5 over minus 5 plus c, and when you work all of these out, negative 3, 5x to the 5 plus c. So I hope this makes some sense to you. So we are using formulas. Integral of 2 plus e to the 3x dx. Okay, let's see what you're going to get there. I'll be right back. Just gonna grab a bottle of water. Okay, I see the good result on YouTube already. So the first one gives us 2x because the derivative of 2x is 2. You can, go that way. And then plus e to the 3x over 3 plus c. All right, very, very good. Now, what are we going to do about this plus c business? Well, let's go back to pre-calculus and review let's use capital F, what f of x plus c means in pre-calculus course. So if you haven't done any calculus, you haven't done any of these things, it's just the pre-calc. So what the pre-calc1 says about this? Well, this means shift up or down. So if you are to have some kind of function there, then you're going to have infinitely many of these blurs like this, and they're actually filling up every single speck of space in here, because they're all clunked one on top of the other, like this, and so now what's important is to understand that this plus c is just going to push them up and down the curve. And in addition to this, you are going to have this fact. When you pick a point, there is only one curve out of infinitely many infinitely stacked curves. Only one will go through that point. So there are infinitely many curves, but only one is given. Now, let me give you an example of that immediately. Remember how we had that x squared problem where we said that x squared blah blah blah. So now, what is the integral of 2x dx? Well, you know, oh, actually, what is the integral of 2x dx given that f of x will go through, and let's just pick literally whatever in here, like 232. It doesn't really matter what you pick. So, okay, let's go and figure it out. Integral of 2x dx is equal to x squared plus c. So now we know that the capital F of x, which is the antiderivative, is x squared plus c. From here, I know that f is 32 and that x is 2. And c, I can compute c. 32 equals to 4 plus c, c equals 28. So, x squared plus 28. See? Now I have the actual function. Now the point that we pulled out of nowhere is the point which we call initial condition. And that initial condition is the point which determines exactly which function out of infinitely many functions is the one that you want. Because, as I said before, only one of them can do this. All right. Let's take a look at another one of these cases. So, integral of secant x tangent x dx, and the point is, let's go pi over 4 and let's say 6. So you have to integrate and then go through all of the other hoops. So let's go. What is the integral of this secant x tangent x dx? Perfect. Plus c. So now I know that my antiderivative is secant x plus c. So 6 is equal to secant of pi over 4 plus c. Now secant is 1 over cosine because we want to compute this mess. So 6 is equal to 1 over cosine of pi over 4. That's the value we know without a calculator, right? So that's 1 over root 2 over 2 plus c. Now, this becomes 2 over root 2 when you deal with your double fraction. And you rationalize this, right, times root 2 times root 2 to get just root 2. So when you rationalize it, which is, what is that? That's intermediate algebra, I think, or whatever. You get 2 root 2 divided by 2 plus c equals to 6. And c is equal to 6 minus root 2. So that's your c. And now you know that the answer to that integral, the antiderivative, is secant x plus 6 minus root 2. You can go get the decimal and stuff like that, but we don't care. Right? It's going to be about 4.6 there. Yeah. So you can use the initial point to compute this. And obviously, you know, many applications. And I think I had a good discussion with the other class. You can go watch that lecture as well, where I went really, you know, far and deep with the concept of kinematics in physics and how all of this relates to, right, your physics courses and later on engineering courses. Now I understand that not everyone is going into engineering and physics and so on, but for those who do, right, it's very important to link this there as well. So kinematics, so motion and so on. Now I'm going to give you, because right, it is the part of the lecture anyway. You have position function. Make sure you're doing this in the middle of the paper. You have velocity function. And you have acceleration function. So, as you are taking derivatives in respect to time, right, you keep getting, right, you differentiate position, you get the change in position, which is velocity, and then you differentiate velocity, and you get the acceleration, which is change in velocity. So acceleration. So now I hope you can understand how this goes, right, with the word change and the derivative and all of that. Because if you want to go with your car from point A to point B and you just get in a car, you're getting nowhere until you press acceleration pedal. Because acceleration pedal, which is gas, is going to change your zero speed to whatever speed. And then you are moving at that speed. And because you are moving at whatever speed, you are covering the distance, which is, right, point A to B. So none of this happens unless you press acceleration. And you can see that acceleration is the one that changes velocity. And then velocity, because you now have it, you're moving, velocity is calculating the change in displacement, which is, right, outside of the physics called, you know, the amount of distance I drove. So all of that is true. Now, if you want to go backwards, you can integrate and you can go all the way back into this. Now, I did give an example of, you throw a rock up and then it comes down and hits the ground. And I gave the, that your acceleration is actually negative 9.8 meters per second. Right? Now, when you integrate that, when you integrate acceleration, you get velocity. So integral of acceleration in terms of time is the velocity. So what I need is negative 9.8 integrated in respect to time, and what you get is negative 9.8 t plus some constant c. So your velocity becomes negative 9.8 t plus, and instead of a c, I'm just going to call it v0, because that's my initial velocity. And then I can integrate velocity to get position as a function of time, which is this part here, right? Where you integrate position. So you see these arrows are coming from bottom to the top, right? So when you integrate this one, you will get the one on top. So now if I integrate negative 9.8 t plus v0. Remember, I have to place all of this in parentheses because I have a times in front of dt. More details on that when we get to 5.2. Relax for now. Just know it's dt has to be there and all that stuff. So now we have negative 9.8 t squared over 2. Remember, you are integrating t. Well, it's the same like integrating x. And you have the charts in front of you, so you can refer to them, make sure. And then we have plus velocity 0 times t plus again some c. Now this is your position function s of t. Now when you fix this, you get that your function s of t is equal to negative 4.9 t squared, right? I had to combine these numbers. So half of 9.8 is 4.9. And then plus v0t plus s0, which is initial height. So here are the three equations for parabolic motion, but also more than that. So the first equation just tells us what the gravity is, and obviously, gravitational pull. And obviously, these things are different for a different planet because it's a different size. So both Mars and the Moon are what? You have position function. Let's go from scratch. You have a position function here, and it depends on gravity. Now, Moon and Mars have lower gravity, which means this number will be lower. 9.8 meter per second squared is on Earth. So when you go through integration and you divide it by 2, you're going to get 4.9. 4.9 is not gravity. This is gravity divided by 2. Now, some of you might have taken physics before, and you have seen the formula written as y equals negative 1/2 gt squared plus v0t plus y0. That's the same formula. It's the same formula. And the gravity right here, I said negative 9.8. So it worked out to be, because it's divided by 2, to be negative 4.9. Now, as I said, for Moon and Mars, right, it's going to be less than that because they have this gravitational pull of 9.8 is smaller, right? So they're going to have a different. Now, the same physics applies but they have a different number because their gravitational constant is different. I mean, not gravitational constant, the gravitational pull on the planet is different, or the surface of the moon is not a planet, it's a satellite. Yeah. So, so now you can see that we can not just go from the position, take derivative into velocity acceleration, but we can start at acceleration and keep integrating up to get into position function. And these are all of the things that you want to know, right? As a researcher, engineer, scientist, whatever, right? You want to know where the particle is, or a car, or a rabbit, how fast it's moving, which is the speed, velocity, and all that, which direction it's moving to, and is it speeding up or it's slowing down, because that's your acceleration, right? If it's speeding up, that means it's under change of speed, and change of speed we defined as the acceleration, right? That's the change of speed. Now, one more cool thing is to realize that you can find the maximum value over here, right? When the rock goes all the way to the top, right? So you want to find y maximum, the rock stops. Okay, what does it mean in numbers and equations for something to stop? Well, at maximum height, your velocity of the object is 0. So you would say, oh, at max, velocity equals 0. Oh, wait, but velocity is the first derivative of position. Of course, that first derivative equal to 0 gives us critical point, which gives us maximum value, right? I mean, we covered that in at least 3 lectures so far, maybe even 4, that derivative equal to 0 gives us maximum value. So what is the v derivative of? It's the derivative of s of t. And because of all of those problems, mean max problems, optimization problems, first derivative test analysis, and when we drew those lines in 3.2, right, when we matched the black function to the red derivative function, right, on the graph, we were using, every time you have a minimum and maximum, draw the 0 on the x-axis. Like all of those concepts are, you see, they all come together. When you learn physics from a concept point, not from the formula point, the physics as a course becomes a joke. The biggest joke, general chemistry, even bigger joke than physics. When you learn them from the point of a concept where you can use the calculus and just say, oh yeah, I remember this one from calculus. Oh, what do I need? Maximum height? Okay, maximum height. Formula that measures the height is this one. That's the one that measures the height. So if I just take its derivative and set it equal to 0, oh wait, derivative of position is velocity. Okay, so set velocity equal to 0. Oh yeah. When I throw something up, when it reaches the maximum height, it stops. Velocity is 0. So it's not even set derivative to 0 or set velocity to 0. You're actually observing it by looking at the thing you throw, right? You're looking at it and you see that it stops right there. Okay, so it stopped at the maximum height, velocity was 0. Now, the fact that all of this calculus and other things click in so perfectly is just because this is all consistent. It is what it is, and it works. So there you have it. Okay. So now, hopefully we understand, right, that given initial conditions, I can calculate exactly where the rock is, which is the position, which is S. I can calculate how fast the rock is moving, and I already know the gravity, right, the acceleration is negative 9.8, so I don't have to worry about that one. That's given in this particular problem. But, throwing something upward is not the only problem in kinematics, right? you can have a whole bunch of other motions, right, that are not parabolic motion with a different type of a function. In which case, right, again, let me integrate, let me differentiate, right, do whatever needs to be done to go from one to another. And this diagram that I have over here is the diagram to guide you through that process. So you say, what is given to me? Oh, velocity function is given to me. Okay, if I differentiate velocity function, right, I'm going to get acceleration. And if I integrate velocity function, I'm going to get position. So no matter which equation is given to you, no matter which equation you can observe in nature, right, you can always get the other ones, because every single one is connected to the others through the derivative and integral. And just, okay, given acceleration, integrate twice to get the other two. Given position, you differentiate twice to get the other two, because that's what the diagram shows, right? I mean, it's not because the diagram shows it, it's because that's the law of nature and mathematics, right, and physics. The fact that I wrote this as some kind of guide is not the reason why these things work in nature. That was kind of silly. Anyway, so if you are given acceleration, you can integrate twice. If you're given position function, you can differentiate twice to get the other two functions. And if you're given velocity, you do one derivative to get acceleration, and you do one integral to find the position, because that you have to go both ways. And yeah, that's it for 4.9. That's it for chapter 4. We ended our derivatives, and now with the antiderivatives, we are opening up a new chapter in calculus, the part 3 of calculus, where we learn about integrals, which will go for most of your, well, not most, like 60% of your Calc 2 is going to be integration. And then that's going to go back to normal to about 40%, right, integration when you go to Calc 3. Even less when you go to differential equations, because we learn other methods, right, in this class. It's still important, still going to be there, obviously, integrals, but yeah. We know that we have to put plus c every time we integrate something, so that's a must. And that's it. So I'm going to open floor for questions. Any questions, concerns? Would you like more problems to practice now in class? Do you have a particular problem in mind? Because you have to be very careful with multiplication. Insanely careful. We do not have integral f times g dx. We don't have that. No, right? Now, there are going to be in 5.5 and 8.2 two techniques that deal with multiplication. Remember, your problem for derivatives had the product rule, and later, ultimately, the logarithmic differentiation to deal with the derivative of a product, which is why it's called product rule. And you had to use the product rule formula or logarithmic differentiation to solve the problem correctly. If you took independent derivatives and you multiplied them, that answer was always garbage and did not carry any points because it's completely wrong. Now, for integrals, we only did basic integrals, so we don't know how to deal with multiplication unless you can cheat with algebra. So now, do you actually have a specific problem in mind? Oh, okay. So I can tell you, like, integral of x squared times x plus 6 dx is okay for you to work on, because you are going to distribute this x squared, get x cubed plus 6x squared, dx. And then you are going to say, okay, it's x to the 4 over 4 when I add 1, plus 6 times x cubed over 3 when I add 1 plus c. And then you just cancel what you can, right? Which gives you, oops, plus, which gives you 2x cubed plus c, and you're done, right? So this is a problem that you can do, but again, I don't want to say you cheated with algebra, but you cheated with algebra. You haven't done the method of calculus in this case. But if you are to have something like this, let's say you have integral of x times sine x squared dx, this is going to be a problem that has multiplication, and it's going to be a problem that it's in 5.5. And a problem with x times sine x dx, which is also a multiplication problem, now there's no squared on x, is a problem that it's going to be in 8.2. This is going to be the opening problem or introductory problem of 8.2 in Calc 2. So you have to be very careful. If you see division in your homework and exams in Calc 1, if you see multiplication, that is either a basic integral or it is some kind of algebraic manipulation. This is the reason why integral of tangent dx is not a basic integral. Because, think about this, integral of tangent x dx can be rewritten as integral of sine x over cosine x dx. And this is division. And this is going to be, again, in your 5.5. So we are going to deal with this integral in our class, but not until after Thanksgiving in 5.5. Now, to contrast this, if you have this as your problem, this is something that you are perfectly fine and able to do because you just know the formula. Right? Yeah, this looks awful, but you know what it equals to because what you memorized is that the derivative of tangent inverse x is equal to 1 over 1 plus x squared. Now, this is actually also an excellent opportunity for me, and thank you very much for the question. It's an excellent opportunity for me to distinguish between students who say, oh yeah, the class is online, the exams are online, I can just cheat using the formula. Yeah, you are going to solve this problem when you cheat using the formula, because you have the formula next to you when you do the exam. The hell breaks loose very quickly in this class at 5.5 when this formula is masked by algebra on top. Now, because you didn't really learn the formula and you don't have enough practice with the formula, knowing that you can cheat, you are not going to be able to see it in 5.5. And obviously, you're never going to be able to see it later on in Calc 2 when problems become way worse. So, as I said before, right, I usually say to my students, C grades in Calc 1 usually don't make it through Calc 2. Now, I have to retire that statement until we go back into classrooms where I know that you are taking your exam without reference. Because now, I can guarantee that we are going to catch A students not pass Calc 2 because they didn't learn anything in terms of formulas and you can't see the form, right? And these are some things that are very important, right, coming into this. So, for instance, integral of x squared over 1 plus x to the 4th dx. Like something like this it's of that form. Yeah, Calc2 and all of this blah 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 stuff that we need to do. But looking at this, oh, not the x squared, x. Is it x? Yeah, it's x. Like you can't recognize this as that if you really don't know this very well and how this thing works. So again, once you get there, you'll see. Right now, right, we are where we are with all of these things. Excellent question. Thank you. That was great. I added a lot more to it to discuss. Now let's see any other questions regarding this introductory. I was thinking also to go through 5.1 today, but as I said, we are nowhere close to being behind or anything like that. I'm not worried about anything, so I'm not going to panic. We don't have to do any of the 5.1 today. We'll do it next class. It's fine. Any other problems or questions on this particular thing? And we still need to vote on the exam, so don't be disconnecting. All right, well, in this case, if there are no questions, you can obviously catch me during office hours and ask more questions. Let's then, I'm just going to delete this thing. Let's then end this and